All right, so questions? ODPs, PAs, whatever.
Make sure you're, I was able to access the readme.
You what?
I can access the readme last night.
Really?
I found it on the video though. Because you looked at it on the screen.
For 211?
Yep.
Well, that's a drag. Should be there, should be readable. That's weird. It's been there since yesterday morning. So what? Okay. Other questions, worries? ODP 211 okay? 212 okay? What is ODP 212? You're doing a little bit of an insert algorithm. So the same tree node, and you're making a function called add. It takes the root of a tree, and a tree only has a root. Okay, so the root has null children, and it takes an integer. You to create a new t node with that integer value, null children, and put it on the correct side of the root. The left if it's smaller than the root's data, the right if it's bigger than the root's data. Yeah?
So when we make this, should we expect it to be the same size as what we worked with yesterday? Just the 3 total nodes? Or is this going to be a single root?
So you're starting with a root. These are null. And there's some data value. That's what's passed to your add function, along with an integer n. So you need to create a new node n, null children, and either, if it's smaller than the data, point to it from the left child, or if it's bigger than the data, point to it from the right child.
So we don't have to check and make sure that we don't have to go down a bunch of our.
The thing you're passed is just a single root node, no children. The thing you're passing back is the same root node with one child hanging off one side. So you're going from a tree of one node to a tree of two nodes.
You want us to test if the number we're given is equal to the root's number?
It won't be. And I don't know what you should do in that case. You can just blow up or something. But I'll make sure it's different.
Can you delete your files if you do that?
You can delete my files if you do that. Actually, this stuff runs as yourself, so it would delete your files.
I'm not going to do that.
Okay, good strategy. All right, so that's 212. It's comparing a number to the root and then adding to the correct child side. So a small piece of well, not so small a piece of your insert function ultimately. All right, questions on stacked queues? Did you get your pop to work? Cool. All right, well, we talked about node deletion yesterday, right? From binary trees, we deleted nodes. And we talked about using the largest number from the left subtree or the smallest from the right.
We didn't talk about deleting.
Did we talk about deletion?
We were going to talk about that today.
It sounded like we just had to go over it.
Oh, okay.
We did insert and the search.
Oh, we were playing with the stack pages.
Yeah.
Cool. Okay, let's talk about deletion then. So we'll put down a tree. clean this up. And there's a nice messy looking tree. And when we want to delete a node from a tree, there's a number of different cases we can find ourselves in. If we wanted to delete the 5, we just change it to null, and we're done. If we want to delete any leaf node, we just find where it's connected to, and we change that to point to null instead of our leaf node. So deletion from the bottom of the tree is very easy. If we wanted to delete the 85, we could just move the 83 up in its place. But if we want to delete the 10, we have to be a little more careful. We could move either the 5 up or the 14 up. But as we move up in the tree, deletion becomes more and more tricky. And the worst case is deleting the root. Because if we delete the 40, what do we put in its place? We could try to move the 60 up there. But 60's already got a left child. Where's the 20 going to go? To the left of the left. Maybe.
But that makes it more efficient.
And we could move the 20 up, but we'd have to do something else. And if this had some other nodes off of it, so let's say this had a 54 and a 56, right? Then we couldn't just put a 20 off the left of the left. We'd have to go left, left a few times and so on. So deleting the root is the hardest part, and the algorithm we're going to talk about first is for deleting the root of a tree. And it'll turn out if we want to delete something that's not a root, we can change that into a problem which is deleting the root of a tree. So let's just delete the root. And this is the algorithm we're going to use. Yes?
I was just curious, I know that they don't do sentinels, and I'm wondering why. It doesn't seem very memory intensive.
Because we're going to mostly use recursive code,
Okay,
and it kind of messes up the recursion. All right, so we want to delete the root from this tree. Here's the algorithm for doing it. And when you code this up, and this will be PA4, so it's a few weeks away. When you code this up, you don't want to do things like, say, if it's the leaf node, then just get rid of it, or things like that. We're always going to use this algorithm for deleting the root of a tree, which is the following. We're going to look in the left subtree and find the largest value and move that up to the root. Or we're going to look in the right subtree and find the smallest value and move that up to the root. So let's try this first approach first. Let's take the left subtree, which is just all of this. And what's the largest node in that tree? It's a 30. So to delete the 40, what we're going to do is remove the 30 and put that up at the root. And now 24 is going to point to null. And that's still a binary search tree. It still has the same order, but the 40 is gone. Equivalently, we could have gone into the right subtree, that's all of this, and found the smallest entry there. So let's say we want to delete the new root, 30. We could go into the right subtree. What's the smallest entry in this tree? 54. We're going to get rid of that and move that to the root. I'll specify. And a lot of times what you'll do is you'll alternate so that you're not just pruning one side of the tree. So every time you delete, you might do from the other side. But I'll specify for PA4 which way to do it. And you can confirm everything to the left of the root is less than 54, everything to the right is bigger than 54. And we know that's going to be the case because we took the smallest thing over here and moved it up, which means everything else in the tree, which is on the right, has got to be bigger than 54. So this still satisfies the binary search tree property. And why is 54 bigger than this? Because originally it was to the right of the root, which means it's bigger than the root, and all of these were smaller than the root. So this is a safe procedure, but it's not always that easy. There's one small complication. So suppose our tree looks like this. And we want to delete the root. And we want to use the largest element from the left subtree. So what's the largest element in the left subtree? It's a 20. So we want to delete this, and we want to replace it with a 20. But now it's pointing to null. So we have the danger of orphaning part of our tree.
Yeah, if in this particular edge case, couldn't you have the 20 point to what it was originally pointing to?
So we can
And then free the node that 20 was originally at?
we can do this. We can let 20 adopt the 10. But what's a general rule for that? So we'll throw some stuff over here on the right that doesn't matter. Go back to our 40. So let's look at this case. So the left subtree is all of this. The largest thing in the left subtree is 27. Okay, so we're going to remove the 27 and put that up in the root. So 27's left child will be 20, 27's right child will be 60. We've orphaned whatever was to the left of 27. But we're going to let 27's parent adopt that orphan. So we're going to take 26 and let that be adopted by 25. Now, is that always going to work, though? And the answer is yes. Why is it always going to work? Because the largest thing in the left subtree cannot have a right child. If 27 was the largest thing in this tree and it had a child to the right, that child would be larger because it's to the right of the root. So once we found the largest element in this left subtree, we know it has no right child. It may have a left child, but it has no right child, which means that its parent, which is losing 27, can now adopt 27's left child. And if the left child is null, then it just adopts a null child, and it looks exactly like we just deleted 27. So there's a few steps here. So to delete the root, find the largest node, we'll call it X, in the left subtree. Have X's parent adopt X left and move X to the root. And there's details in here, and we'll go through some of this when we look at algorithms for this in terms of pseudocode, but this is the basic sketch. But when we say move X to the root, what we mean is don't just copy the data value, because that data value could be huge, could be millions of bytes. What we mean is take the node X, have its left child point to whatever the old root's left child was. Have its right child point to whatever the old root's right child was. Okay, so take that whole node and sort of structurally plop it into where the root is by having it point to the children of the root. And then the parent that was pointing to that node X now points to what was X's left child, and X had no right child. So all of X's children are taken care of, and the largest node in the left subtree is now at the root. So that's the basic algorithm for deleting a root, but there's a lot of little details in here. which we don't need to get too bogged down in today, but for example, what if there's no left subtree of the root? We can't find the largest element in the left subtree because the left subtree is null. So in that case, we could find the largest node in the right subtree, or we could just remove this and say this is our new root. Either of those will be fine. So if we do that, we end up with this. If we use our strict algorithm, and I misspoke a moment ago, if we take the smallest thing from the right subtree, that would be a 50. We move that up to the root. And now we get a tree that looks like this. In terms of the data stored in here, it's exactly the same. 50, 60, 70 in increasing order. But we get a different shape out. The next question is, how do we find the largest node in a left subtree or the smallest node in a right subtree? So with this tree here, we decided 27 was the largest node in the left subtree. How do we find that? Always go right. So move into the subtree and just go as far to the right as you possibly can, which brought us down to a 27. And we know that's got to be the biggest. Each time we go to the right, we're moving to something bigger than where we were. And when we can't move right any further, we know there's at most the left subtree, everything there is smaller. So to find the largest node in the left subtree, first we move to the left, if there is a left, and then we start going to the right. And it may be that our tree looks like this. And the largest node in the left subtree will be 30. And what we did was we moved to the left subtree, and we found right off the top we could not move to the right. And so this became the largest value. That's going to be another edge case when you code this. So this is going to be a lot of edge cases. And that's part of what makes it challenging and rewarding to code. So we'll have to be a little careful with finding this largest node in the left subtree. And there's a symmetric algorithm for all of this, which is working on the right subtree, right? Anything else I wanted to say about that? So that's for deleting the root. And of course, if our entire tree just looks like this, and we want to delete the root, that's another edge case. The new tree is just null, because there's no left subtree or right subtree to work from. But if you have no children and you're just the root and you're being deleted, then the resulting tree is null. But it's still a case you'll have to code separately. Well, what if you want to delete something other than the root? What if you've got your original tree and we want to delete the 55? That's what the recursion's all about. So let's write a delete routine. So this is going to return a pointer to a tree node. Why? Because sometimes the root of the tree will change after a deletion, right? If we're deleting the root, or if we're going to an empty tree because we deleted the only node, then we've got to get back a different pointer to our tree. So delete's going to return a pointer to the possibly new root of the tree after the deletion, and it takes two arguments. It takes a pointer to the root, and let's just say it takes a number, which identifies the node we want to delete. Okay, well, if that number happens to be at the root, do everything we just said. Largest thing in the left subtree, move it up, adopt the child, all that kind of stuff. So do all that stuff for deleting the root. Okay, so this is delete root.
But even then,
It isn't.
alone, the only.
Yeah, that's part of everything that we just discussed. So all that stuff comes into this one case where we're deleting the root. Okay, and return whatever you're supposed to return in that case, the root of the new tree. Okay, otherwise, we're not deleting the root, so we have a pair of cases. If root data is bigger than num, so the number's smaller than the root, so it's somewhere in the left subtree. So delete from left subtree. We're just going to say delete root arrow left, comma num. So we're going to use our delete routine, and we're going to say delete from the left subtree. And that's going to return the possibly new root of that left subtree, which means that should be what root points to on the left. And then we're going to return the root. So if our number's smaller than the root data, call our delete routine to delete the number from the left subtree, take the tree it returns, and make that the left child of our root, and then return the root. Otherwise, delete from right. So here we say root arrow right equals delete. And then return the root. So there's a sort of 3-case delete algorithm. And that first step, unlike our other recursive algorithms, has a whole lot of work in it. Okay, it's all the edge cases, all the special checks, all the movement around of nodes and adopting of children. But if that's not the case, if we're not deleting the root, we just call ourselves with a smaller problem. And again, as long as we believe that these work correctly, we can firmly believe that this and this will work correctly. Okay, that's the recursion thing. So questions there? Like I say, when we get to PA4, we'll go through all this in a lot more detail. But I'm just kind of giving you an idea of how we do these basic things on trees. So here's a binary tree, and it's got 15 things inside it. It's a binary search tree. And suppose we want to search for some number in here. We're going to compare to the root, and assuming it's not at the root, we're going to move to either the left or the right. Let's say we move to the left. We'll compare our number to this, and if it's bigger than that, we'll move to the right. And if it's bigger than this, we'll move to the right, and either this will be our number or it's not found. Okay? We need to do a total of 1, 2, 3, 4 comparisons, worst case. It might be our numbers at the root, or it might be it's bigger and it turns out to be right here, and we only had to do 2 comparisons. But worst case, we have to do 4 comparisons. Now, we could have the same set of 15 nodes in a really unfortunate tree, like this. And worst case, our number's not in here, and we have to do 15 comparisons. And that's just a linked list. That's our order n search operation. exactly the same set of data, exactly the same search order, both binary trees, but this one is going to be much more efficient than that one. So we want our trees to look more like this and less like this. And the main reason that this is more efficient is because it's shorter. So we talked about the height of a tree, right? The height is the depth to the deepest node. Well, the deepest node here is all the way down here. If you count the number of edges, that's the depth. It's 14 or 15. Here, the deepest node is only 1, 2, 3 steps from the root. So the height of this tree is 3. The height of this tree is 14. So if we can somehow minimize the height of the tree, we minimize the number of steps that you need to make. Because the number of comparisons you have to do is exactly the number of nodes that you visit from the root to whatever it is you're looking for. And if the height is only 3, we know that the maximum number of nodes is 4. The maximum depth is 3. So we'd like our trees to have a really low height. And the term we're going to use is balanced. So we want our trees to be balanced. And in some sense, this tree is very unbalanced. All the stuff is on the right side of the tree. Nothing is over here on the left. And this node right here only has things to its right. It has nothing to its left. So this is about the most unbalanced tree you can imagine. It's totally lopsided one way. This is perfectly balanced, right? Every node has exactly 2 things on each side or exactly 0 things on each side. And if we were to get rid of this node, it's still pretty balanced, right? But this node only has 1 thing on the left and nothing on the right. And if we were to hang something down here, this node's also unbalanced. It's got something on the right, nothing on the left. It's still better balanced than this, but is it as well balanced as it could be for this set of data? So let's look at a way to define when a tree is balanced. So a binary search tree, T, is balanced if the following conditions are true. Look at the height of the left subtree, and look at the height of the right subtree. Take their difference and look at the absolute value of that. That has to be less than or equal to 1. So the height of the left and right subtree have to be the same or within 1 of each other, which is where this tree fails miserably, right? Because the height of the left subtree is null. Its height is technically -1. The height of the right subtree is 14. Okay, really far off. So the left and right subtrees need to have heights that are the same or within 1 of each other. But that would also, by itself, here the left subtree is right here. That has a height of 4. The right subtree is here. That has a height of 4. They have exactly the same height, but this doesn't feel like it should be balanced. So we need some additional properties here. So and the left subtree is balanced. And the right subtree is balanced. So there's our definition of balance. Surprise, it's recursive. So left and right subtrees have pretty close heights, and the left subtree itself is balanced, right subtree itself is balanced. So it's recursive, it's a self-referential definition, but it's not a hopeless one because T left is a smaller tree than the original tree. It's not including the root of the original tree. So if we write code for this and we look at the heights and we say, okay, those are close, then we're going to look at the left subtree and we're going to call our balance routine to see if that's balanced. That's going to be a smaller tree. Okay, so each time we call balance recursively, our problem will get smaller and smaller. But what's wrong with this code as it is, this definition? Why is it going to seg fault? It doesn't have a stopping point. It doesn't have a base case. Eventually, since we keep looking at the left subtree of the left subtree of the left subtree, eventually that's going to be null. And if we try to look at null arrow left, there's our seg fault. So it's balanced if all of this is true or t is null. So two ways a tree can be balanced. And a null tree is defined to be balanced. And it's just a definition. It has no children. We can't talk about its left subtree or its right subtree or its root. But we define a null tree to be balanced. And this is really easy to code, right? It's one big if statement. If t is null, return true, else if height is less than 1 and t left is balanced and t right is balanced, return true, else return false. So what does this look like? So a null tree, is that balanced? Sure, that's our edge case. What about a tree with a single node, just a root? Right? The left subtree is null, that's balanced. The right subtree is null, that's balanced. The height of the left subtree, the height of a null tree is -1. So let's remember that. The height of a single node is 0. And the height of something like that is 1. So it's the number of hops from the root to any node. So that's 0, and we define null to be -1. And that'll make our height function really easy. So this is definitely balanced. What about this? It doesn't feel as nice and full as it should, but in fact the left subtree is a single node, which is balanced. The right subtree is null, which is balanced.
It is only one path, so.
Yeah, so the height of the left subtree is the height of this, that's 0. The height of the right subtree is the height of null, that's -1. 0 and -1 differ by 1, so that's balanced. And certainly this will be balanced. So what about this? That's going to be imbalanced. The left subtree is balanced. The right subtree is null, that's balanced. But the height of this tree is 1. The height of this tree is -1. They differ by 2. So that's not balanced.
So if you added another node on the right on that one, that would become that.
So if we have this, balanced, balanced, height of this node, this subtree is 0, height of this subtree is 1, that's balanced. And in fact, left and right subtrees have the same height. Left subtree is balanced, right subtree is balanced, that's also balanced. So our intuition doesn't always work. But if we add another node down here, like this, the heights are still within 1, but the left subtree is not balanced. So that's enough to say this is not balanced. So generally, we're going to want to fill up the higher layers before we start adding to the lower layers. And in fact, if we started with this tree and we wanted to add one more node, there's nowhere we could put it except as a child of one of these. And as a binary search tree, we can't insist that this node's going to come off this parent, because if it's bigger than this number, it's got to go to the right. Okay? But once we get to this, there's some flexibility to how we could draw this tree. So let's look at this last imbalanced example. So here's a 40, a 30, a 20, here's a 50, and a 60, And let's add a 10 to this tree. So just starting with the root and moving left, right based on comparisons, we'd come down to here and we would add a 10. And this tree is not balanced anymore. But it turns out, since it was balanced before we did this, we can make an adjustment to this tree and restore the balance. And the basic idea is this is the problem, right? This is hanging too far to the left. But this tree is equivalent to this tree. But this one is very left heavy, this one is balanced. So we could take this original tree and change it into the following. Instead of 10, 20, 30, let's have 20, 10, 30. And bingo, that's balanced. So here's where we're going to go in a few weeks when we come back to this. As we insert things into trees or delete things from trees, our tree will sometimes become unbalanced. It'll be lopsided one way or another. If at the point where we've made a change to one node, we introduced an imbalance, we can always correct it with a minimal amount of work. 1 or 2 operations.
So is there for like such as like insert all numbers and then make it balanced is the goal of this one?
Say again?
I mean the goal of this one?
The goal is to insert numbers and keep your tree balanced.
But like at first I think like at first make the structure all balanced all like tree and we can insert some number all and on the
If you have a balanced tree, you can insert a number and keep it balanced. But what we don't want to do is insert a bunch of stuff into a tree and then try to balance it. Okay.
For example, like if I use for loop and like it's like a lot of at first make a lot of like structure
Mm-hmm.
and for the like for all number for insert number
Mm-hmm.
and find out the half number of all series
Okay.
and insert the root
Mm-hmm.
and the remain like right side left side and half and insert the other one.
But after you've already got the structure of the tree, it's fairly cumbersome at that point. So the algorithm we'll talk about assumes that your tree is balanced to begin with, and you're adding or removing one number, and it'll tell you how to keep it balanced after that. If you add 2 numbers and then say, is my tree balanced, and it's not, you might have a complex task to rebalance it, right? So the idea will be to keep your tree balanced after each single change to it. So in this case, right, this tree was balanced, we added a 10, it wasn't, we'll make this one correction to here, and now we're balanced again. And as long as it was balanced before we did that insert, we'll be able to do this with 1 or 2 operations, and these operations are called rotates. And they're basically things like going from this to this. Mm-hmm.
So you know how on the right side it goes 50, 60, and then the left side goes 10, 20, 30? What if you add like another one to the left side and you just keep adding like 3 numbers, for example, to the left side? Would
So-
that just come from 20 or?
So,
Would it be possible to balance
Yeah.
that? Like,
yes.
I already, you can move that up to the root and you can change what the root is in order to balance it, right?
So if we add a 5 here, we'll have to do something else. But again, with 2 operations, we'll be able to restore a balance to this. And this may still be balanced. And then we'll add a 3. And then at that point, this will become 40, 50, 60, 20, 30, 3, 5, 10. And then if we keep adding some more things over here, at some point we're going to get to a case where we have to do 2 rotations. But 2 is always the worst case. Yeah.
So does the rotate operation include setting the parent of 20 in our example? Or is it just having to do
It's changing what 40 is pointing to, so that instead of pointing to this, it's pointing to that.
Okay, so the rotate operation where it's on, in this example, 4. So that's,
Yeah. So the rotate is basically we've got number, number, number. We're going to change it to look like this. Or if it was number, 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 we would change it to look like this. But sometimes there's a secondary operation you have to do. If your tree is left heavy, but within that left tree it's right heavy, then you have to do a pair of rotates.
So, cases where, like what you mentioned, 2 rotates, but would there be an advantage to moving stuff from the left subtree up to the root, moving the root to the right?
That will happen in some cases. Right, so it depends where your imbalance is occurring. And this is recursive, right? So sometimes you have to chase your balance point up the tree. But certainly if you keep hanging things way off the left, at some point you're going to have to change the root, right? Because the root's the biggest, but it can't stay at the root. It's going to have to come down onto the right side. So this can drastically change the shape of the tree. But this is an exercise in special cases. Okay, there's 4 fundamental cases to deal with. They're symmetric, but then within each of those cases to actually implement it, there's a bunch of edge cases to deal with. I may or may not have you code that up. I've never assigned it, but this class is rocking, so I might assign it.
So, how would delete influence this?
Delete's the same thing. When you delete from a balanced tree, you can become imbalanced. And we'll talk about something called a balance factor, which at each point measures how unbalanced the rooted tree is from that point down. Yeah, each node has a balance factor. And you can adjust these balance factors following an insertion or deletion. And there's ways to do all of this efficiently. And that's part of what makes the coding part tricky, or trickier. All right, so we'll discuss balancing trees in a few weeks. And this way of doing rotations is something that we call an AVL tree, three mathematicians, AVL. It's one way to maintain balance. There's another thing which is called a red-black tree, and we'll talk about red-black trees. And it's a totally different feeling from AVL trees, and it's really kind of wonky, and that's where we get into siblings and grandparents and uncles and aunts and things like that. So we'll play around with those in a few weeks, or in 223. We'll see where we get to. Let's look at height. The height of a binary search tree somehow we've got to know that this is the deepest node, and we've got to calculate its depth, which is 1, 2, 3, 4, 5, and say the height equals 5. And we can do this by traversing the tree in any order and having maybe a global variable, maximum height, and each time that we step down to a child, increasing a local height measure to know the depth of each node, and at each point comparing that to the maximum height we found, and updating this global, and when we're done traversing, whichever was the deepest node would have set the value of the height, and that would give us the height of the tree. So that's one way to do this, but there's an easier way to do this, which is if we look at this entire tree, we can think of this as having 2 subtrees. Well, if the height of the entire tree is 5, one of these subtrees must have a height of 4. In this case, it's this tree has a height of 1, 2, 3, 4. There's the deepest node, depth of 4. Now, it could be that both subtrees had a height of 4. But if this subtree had a height of 5, the height of the whole tree would be at least 6, because we're adding one more node on top of it. And if neither of these had a height of 4, there's no way that the entire tree could have a height of 5. If this had a height of 3 and this had a height of 2, the height of the whole tree would only be 4. So we know that if we look at the height of the left and right subtree, at least one of those is exactly 1 less than the height of the entire tree. So that gives us an idea for finding the height of the tree at root. Let h1 be the height of the left subtree. Let h2 be the height of the right subtree. If the left subtree is the one with the greater height, just return its height plus 1. Otherwise, return the height of the right subtree plus 1. And what's our edge case? What's our base case here? If the root is null, that seems to always be the case. And our definition of height for a null tree is -1. There's a full height routine. And the only math we ever do in here is we add 1 to something. And there's no looping, and there's no traversing, right? It's magic. But that will absolutely work. As long as, again, we believe that these functions do the right thing, then this function does the right thing. And we know in our base case where the tree is null, height does the right thing. And we can work up inductively from there. So there's how we can calculate height recursively. So this is why recursion is so key for dealing with trees, because all these functions become really, really trivial to write and trivial to think about if we think about them in this recursive way. And all we're doing with recursion is breaking a big problem down into smaller problems, using the solutions of those smaller problems to somehow get the solution of the bigger problem. That's the essence of recursion. And the joke is the key to understanding recursion is to understand recursion. Same thing. All right, so there's the height function. So Monday is your midterm, so no lecture. Tomorrow you come in, talk about projects and stuff. Tuesday we will look at some other applications of trees. And then we're probably going to switch over and talk about hashes. And we'll spend some time on hashes while you're finishing up PA3 next week. And then the following week we'll start working on trees in more detail. All right, I will see you next time.